Thank you so much, Sherry. Good morning, everyone. I'm Sarush Sarushian. I'm the current chair of the Rosenberg International Forum on Water Policy, and it is my pleasure to welcome you all, depending upon where you are in the world. Either it's good morning or good evening or good day. We'll leave it at that. I think some of you participated in our first Zoom conference. Traditionally, Rosenberg Forum has a biannual meeting by invitation, and unfortunately, the one that was scheduled for a few months ago in China had to be canceled because of the pandemic. We hope that we can reestablish and go back to normalcy in the very near future. So you probably have read a little bit about the background of this particular activity through the University of California Office of the President, and particularly handled by the Ag and Natural Resources Division. If not, there is ample information on the website. And this will be our second one, and I'm delighted that I'm joined by two distinguished colleagues who will be introduced by Alberto and the people who are going to run the program. At this point, I welcome you all, and I ask my dear colleague, Glenda Humiston, who is the Vice President of the University of California System for Ag and Natural Resources, to say a few words, and then we will proceed to the next step.
Thank you, Sarush, and welcome to everybody that's joined us this morning. I'm Dr. Glenda Humiston. I'm the Vice President of UC's Agriculture and Natural Resources. The Rosenberg Forum is one of many statewide programs we deliver here in California. This one is really exciting for me because it's one of those opportunities to bring together scientists, policymakers, and thinkers around the big water issues from around the globe. And it's real exciting to see who all has joined us here this morning. For those of you that did not join us in the first one, where we really looked at a large picture of what's in the world of water, the chat room will have a link to that webinar, which was recorded. Today's will be as well for others to enjoy. And I really encourage you to think about joining us in February 4th for our third one. This is one of three that we're hosting. And as Sarush said, we're looking forward to actually being able to meet in person again in China next year, once we get the pandemic under control and better managed. So with that, Sarush, let me throw it back to you. And once again, welcome to everybody. We're really thrilled to have you with us this morning.
Thank you, Glenda. I appreciate your remarks. I guess the next thing I have to do, and it's my pleasure to introduce the members of the advisory committee of the Rosenberg. I am guided by their wisdom as how we should proceed, and the staff that are involved in helping us. Unfortunately, two members of our advisory board, Ariel Dinar and Helen Ingram, had other commitments way before we set up these times that could not join us, but the rest of the members are hopefully here, and they will introduce themselves if they've already joined, as I see. So I will start with Christina. You want to say a word or two, and then please, each one of you say a few words.
Good morning, everyone. From San Francisco, California. I work for Environmental Defense Fund, and I manage our California groundwater program. It's wonderful to have everyone here today.
Okay, good afternoon from Spain. I am Lucha De Stefano. I am Associate Professor at Universidad Complutense de Madrid, and I am Deputy Director of the Water Observatory of the Putin Foundation.
Qin Yunduan from Huahai University. I'm a hydrologist at College of Hydrology and Water Resources in Nanjing, China.
Good morning. My name is Alberto Garrido. I'm a professor of agricultural and natural resource economics at the Universidad Politécnica de Madrid, Spain, Technical University of Madrid, Spain. and also I'm the director of the Water Observatory of the Botín Foundation.
Okay, I assume that perhaps Andrea has not been able to join us yet, but when they do, they will probably participate, and Ayman also. Doc Parker, who is also an ex officio, unfortunately, is unable to join today, a loss of his father in his family. But the rest are here, and Sheria has already introduced herself, and maybe Julia, Rachel, you want to say a word so people recognize you? Silence.
I think they're focused on their task.
Oh, they're on task, but everybody can see them. All right. Well, with that, I guess we are ready to launch into the program today. And at this point, Sherry wanted to also share that we have representation or people that are participating for 39 countries. And I'm sure that as Zoom meetings go, people come in and go depending upon the time and the commitments they have. So we are thankful that you are participating in today's webinar. With that, I will ask my colleague Alberto Garrido to take over and move forward with the program.
Thank you very much, Suruz. We will introduce, as the program indicated, 3 presentations, and starting with the introductory one by Dara Entehabi, who is Bacardi and Stockholm Water Foundation's professors at the Department of Civil and Environmental Engineering and Earth, Atmospheric and Planetary Sciences at the Massachusetts Institute of Technology. Dara will give us a talk about the new types of observations for hydrological hazards and water management using remote sensing instruments. Dara will make his presentation, and we will take just questions and answers for clarification at the end of his talk. But remember that we will have a discussion at the end of the 3 talks. So questions and answers would be for clarifications only. So with that, I'm very pleased to introduce Dara, and we will give him the floor so that he can present his talk. Thank you.
Okay. Thank you very much, Alberto, and I thank the advisory board and Suruz for inviting me to give this presentation here today. I really appreciate the time that people have put in, calling from all over the world at different hours, so I really appreciate it. So I'm going to talk about new types of observations. The key word is types, because we're going to look at changing the platform from in situ to remote sensing. And the question is, what does that really imply or mean? And to begin, just want to note that water resource management and hydrology as 2 disciplines really grew up together. They were born together, they have a shared history, and they have interacted with one another over the years. So, for instance, the needs of water resource management have driven developments and in hydrology. So, for example, a key question has been for a long time, how much water is available for withdrawal and use. Therefore, hydrology has responded by focusing on stream flow, and the runoff volume is bounded by precipitation. So observations of precipitation are given very important weight, and they're primary. And then to go from precipitation to stream flow, there is a delay. So the water is put through a series of reservoirs to dampen and delay the output. So to predict the The result is the conceptual hydrologic model, like you see an example of on the right. Maybe I can use my arrow. Okay. So the key thing about this is to note that at the very top, the entry point is rainfall, and at the very bottom, the exit point is stream flow. And there's a number of internal variables, storages, soil storages, that function to dampen and delay the output. So the requirements on hydrology and hydrologic modeling has been to characterize the precipitation input and measure the output, because those are the two ends of this system. And the processes that need to be captured are rainfall runoff transformation, routing, and then calibration of the parameters associated with inside guts of this model. And the observations are then primarily the input precipitation that we've traditionally measured with precipitation gauges, and stage output stream flow that allow us to calibrate the system. But more importantly, in order to link the input and output and close the water balance, we have defined a fundamental unit of analysis, which is the watershed. It's very cleverly defined. It ignores political boundaries and all sorts of other boundaries. It basically is the area contained within this topographic ridge, which then means that there's no flux across these boundaries. And there's only flux at the outlet where you put the stream gauge. So this is a natural control volume that we have been used to. But over the last few decades, the driving science questions or the driving needs of water resource management have changed. And at the same time, the capability to make measurements have changed. So whereas before our questions that I just posed a few seconds ago was how much water is available for withdrawal and use, the questions of water resource management right now involve phrases like this: equity and rights, ecological fragmentation, integration with urban landscape, water cooperation, climate change impacts. So really the questions of water resource management have changed, and therefore hydrology has to respond and change as well. So again, these are the sort of the new phrases. This is our conceptual fundamental unit. And if we look at some images, this is two images of land surface temperature. So it's a physical response of the surface. One of them is across the Sinai-Negev border, and another one is in the US-Mexico border. So these are, again, temperatures. So it's physical response of the surface. And clearly, political boundaries do matter. So the fundamental unit of analysis that we so cleverly taught ignored political boundaries is really shown in the physical system here. So one-to-one, the new sort of questions in water resource management, equity and rights, means that political boundaries need to be considered. So we need to change our actual unit of analysis to geography and not watershed ridges. Ecological fragmentation means that we have to also directly observe what the land is being used for. Integration with urban landscape is very clearly shown in the US-Mexico border, where the urban landscape is visible. And water cooperation means we have to draw the political borders. And climate change impact means that it can't just be water balance. We have to also look at the energy and carbon balances at the land surface. So if we go to remote sensing to deal with some of these, meaning actual geography, vegetation, surface energy balance, remote sensing platforms are ideally suited for that because they're mapping instruments and they measure radiation as well. So there's always a trade-off in changing the platform and taking it up to space. There's the trade-off between spatial coverage, spatial resolution, and temporal refresh rate, how often you revisit the same site. So in remote sensing, the world is happy with spatial coverage. That's one thing that it's designed to do. It maps the world. Temporal coverage is also reasonably captured with remote sensing. But when it comes to spatial resolution, there's horror. You know, the remote sensing measurements are tens of kilometers sometimes in terms of their spatial resolution. And that always poses a barrier to adopting remote sensing measurements. But I think it's really shouldn't be there. The question is, what do we have right now? Is the distance between gauges any less than the spatial resolution of remote sensing images? And also, what we gain is the spatial coverage, not necessarily resolution. So, and also a question is, what do we do if we have more and more higher resolution? Can we actually use it? And I was reminded on this very short essay, one paragraph from Jorge Luis Borges, the Argentinian writer, and it's called On Exactitude in Science. And I'm not going to read the whole thing, but it's just one paragraph essay. And I think it's telling about the issue of resolution. It's a story about an empire that had a guild of cartographers, and they attained such perfection that they struck a map of the entire empire whose size was that of the empire. So each point on the map corresponded to a point in the empire. But future generations saw that the vast map was useless. There was no way of using it. So now in the deserts of the West, there are tattered ruins of that map covering animals and beggars. And the lesson for us, in all that land, there is no longer relic of the discipline of geography. So back to hydrology. Okay, so these are available observations, but now we have platforms that allow a vastly different approach to making measurements. These are transformative changes in measurement technologies. And what I'm going to argue that they allow and almost require new conceptual frameworks for hydrology in support of water resource management. Another digression, hydrologists have introduced many models, but just like in nature, there's a natural selection. Those that survive work best with the input and output that we're given, precipitation and runoff. So just as Darwin's finches, they sort of developed different types of beaks or different shaped beaks, depending on the food that their environment provided. So conceptual hydrologic models have evolved into digesting precipitation and stream flow measurements and nothing else. And therefore they're very good at those, but that's the shape of their beaks as we have today. So what's gonna happen when we give them a new type of data, namely remote sensing data? So I work on this project, so for me it's obligatory to give an example out of what I exactly mean by changing conceptual frameworks. So this is a mission that's been going on for 5 years. It uses a very large antenna and microwave radiation to measure, as the name suggests, surface soil moisture. So we have 5 years of global maps of surface soil moisture. And I'm going to go back to the conceptual hydrologic model. Again, the input was rainfall and the output at the bottom was stream flow. And what I'm going to argue is that we need to exactly turn this model inside out, literally, meaning all that stuff that was in the middle has to come out and be on the outside, the interface with the measurements. So to give you an example, here's just one pixel of measurements with the satellite mission that I just mentioned. is volumetric surface soil moisture over a period of several weeks. And the soil moisture goes up and down with respect to rainfall and evaporation and drainage and so forth. So this is the raw observations. If I take the derivative of this to look at the changes, there are periods of dry down that start with very fast dry down at the beginning and then less and less until the next rain event, the positive or rain events. So this is the change in soil moisture between any one of these purple dots. Now, if I plot the probability distribution function of all the negative ones and all the positive ones, so the PDF of the blue and the red, they have the same mean because this time series is stationary. The water doesn't indefinitely accumulate or decrease. It goes up and down around an average. So they have the same average, but they have a very different distribution. That's curious. There must be some information in there. How can we extract that information? If I look at any one of these dry downs, the red dots, they look like this. At the beginning, right after the rainstorm, the drainage is very fast until it reaches field capacity. That's a sort of a agronomy or agriculture variable. That's field drainage under gravity. And then there's a period where drainage stops. Gravity is no longer able to pull the water out of the soil column, and evaporation takes over. But the evaporation is a constant. It's a straight line in reducing the soil moisture because it's very wet and it's energy limited. It's potential evaporation. And then at a certain threshold, soil moisture pulls the water and doesn't allow it to evaporate as fast. So the rates of dry down becomes less and less. So if I look at the losses, that means the slope. It beginning with drainage when the soil is wet, it's very fast, then potential evaporation, just energy, available energy, and then soil limited evaporation. So this loss is the change in soil moisture over time, what I showed before, conditioned on this value of soil moisture. So this is from the data reconstruction of this curve. So now we can delineate when is the surface hydrology in drainage mode, when is it energy limited evaporation, when is soil limited evaporation. And we can map that. So these are maps of percentages of time in each of those regimes. And curiously enough, these regimes boundaries move from year to year and week to week and month to month. So we can now track how the hydrologic regime is changing. Back to this, instead of just calling it a loss, I want to separate it into processes, evaporation and drainage. So let's define very general functions. A loss function for evaporation that has the energy limited and the water limited, and according to a parameter B, it can be anywhere in this domain. Drainage is the unsaturated hydraulic conductivity, so it's power law. Again, the parameters allow it to be anywhere in this space. And we estimated using the same data time series. And here you see the total loss, evaporative loss, and drainage loss. Drainage mostly during rainstorms, evaporation following rainstorms, and so forth. And now we can map evapotranspiration and map drainage across the landscape. And we can compare it with in situ flux towers. They're not exactly compatible. One of them is a pixel several kilometers, and one of them is a point. And also with stream flow gauges over the USGS over the US. And again, neither of them is true, but the coefficient of determination between them is around 70%. And last point is that what actually causes hydrology is therefore these loss functions and the probability distribution of soil moisture. And for instance, in this example, 76% is evaporation, 20% is runoff. And year to year, this PDF moves left and right. But the fraction that is, this fraction is changing with the precipitation in that year. So what this shows is the nonlinearity in hydrology, that the partitioning is actually dependent on the state of the system. So this is with gauges, the green ones, USGS gauges, the blue and the black are from the remote sensing. So we're capturing that. So to close, the concerns of water resource management have changed, and as I argued in the beginning, and also that means that we have to fundamentally change our unit of analysis. We can no longer stay within the boundaries of a watershed, but we need to look at actual geography, actual ecology, actual surface energy balance. And also new types of data are becoming available, and with the new fundamental unit of analysis and the new types of data, we have to completely retool our conceptual frameworks as well. Thanks for the opportunity, and I hope I stayed within the allotted time.
Thank you very much, Dara. Being a practitioner of water footprint, I feel very humbled from your talk and from your analysis. How simple were my analysis. Thank you very much for this. You were very clear, despite the fact that your modeling, your use of data, it seems sophisticated, but I think you made your case very, very clearly, and your message was also very clear. So we have, we know you have to leave in 3 minutes. There might be some clarification questions for you. So let's see if there is something from the audience, and if not, I'll make I'll send a question for you. Let's see if that there is some. Apparently, there's no clarification question, if I'm not wrong, with the system. So, so in terms of water management, what do your models provide? What are the changes that eventually your methods and your new data will provide to water managers?
Yep, I think the mapping capability is sort of the fundamental advantage of remote sensing, that you can actually map variables, and also the ability to map not just the water variables, but the land use. What are the contrasts in land use, gradients in land use? So when we talk about ecological fragmentation and land degradation, that we can actually map those ecological variables. And also surface energy balance. What is the impact on the evaporation at the surface and the sort of the climate, microclimate of the surface?
Okay, thank you. Okay, we will show you the questions and answers that we've been collecting through the talk. Perhaps, Sherry, you could show some of the data that we have with respect to some of the questions that we placed before. So yes, clearly most of the attendants believe that remote sensing observation are promising with respect to any of the audience participants' discipline. So clearly there seems to be an acceptance and a clear view that remote sensing will provide views for improvement for any particular discipline related to water. So clearly, this is something that confirms that your approach is very promising.
So Alberto, there are a couple of questions in the Q&A now.
Okay. Yes. first question, how accurate is this chart data collected from space?
Okay. Currently, direct measurements of discharge or dedicated measurements of discharge data are not made from space. But there is a mission coming up in a couple of years called SWAT. It's a NASA mission that measures the height. Basically, it's a stage measurement from space. And that allows estimation of discharge from large rivers. So there have to be a couple of 100 meters across in order for that. I'm not aware of what their accuracy estimates are, but that's a forthcoming mission. It's the SWOT. If you want to Google it, then I'm sure there's information.
Thank you. I don't know if you have a couple of more minutes for two more questions.
Yes.
The second question is, what new technologies are yet to be deployed to satellite? This person keeps hearing about hyper and multispectral sensors being deployed to space.
Yeah.
David Hill?
Yes. There's no end to the imagination of engineers developing instruments, and there's very interesting set of instruments that are being developed all around the world by space agencies. There's a class of missions that are called explorer missions, and those are sort of technology demonstrations. And then there are systematic measurements. So those exploratory measurements are really wild ideas that are out there. Hyperspectral measurements, there've always been interest in that. One constraint has been the volume of data to download, but there are also technological developments in data downlink, and hyperspectral measurements and high resolution radar measurements are before they were constrained by how much you can bring down data, but that limit is being lifted. So we're going to see more and more hyperspectral and multi-channel instruments.
Thank you. One last question by Abdullah Al-Musa. Does your model can your model be applied to the concept of water productivity?
I have to admit my ignorance that I'm not familiar with the concept of water productivity. So I can't answer. Yeah,
Okay.
my apologies. It's just outside my domain.
Okay, excellent. Well, there seems to be no further questions to you, Dara. Again, thank you very much for your wonderful presentation, for your ideas, and for your messages in terms of rethinking hydrological models and hydrometeorological models now that we have new data. You made your case very clearly, and I think it was a wonderful presentation. Thank you very much.
Thank you for the opportunity, and thank you everyone for their time.
Wonderful. Okay, now we move to our second talk. Let me introduce Cecilia Tortajada, an old friend of mine, I can say, who is a senior research fellow at the Lee Kuan Yew School of Public Policy at the National University of Singapore, and professor designate at the University of Glasgow in the United Kingdom. Cecilia will present her talk about artificial intelligence for water-related sustainable development goals, policy implications. Cecilia, the floor is yours, please.
Thank you. Thank you very much, Alberto. And thank you very much for this opportunity to participate today. The topic, as you were mentioning, I will be talking about is on artificial intelligence for water-related sustainable development goals. And what are these policy implications or policy considerations? And if I can have help to go through the slides every time I indicate this, I would help a lot. If we can go to the second one, thank you. So what artificial intelligence is, we know, is that it refers to the ability of machines to perform tasks that normally require human intelligence. And these include recognizing patterns, learning, drawing conclusions, making predictions, and taking actions, or perhaps not, because at the end, the action that needs to be taken is that of the manager. As the previous presentation of Professor Dara, which was excellent, he explained there are political boundaries and there are political decisions, and they will prevail over artificial intelligence. In the next slide, what we see, thank you. So we come back now to the topic of artificial intelligence. How can this new tool, how can this new technology can help us towards the achievement of water-related sustainable development goals? And what are the policy implications or considerations we have to consider? And for this, we will first have to realize what is this sustainable development goals in terms of water. And in the next slide, what we see is what United Nations say, that is the goal for water is to provide clean water. This is water that can be drunk from the tap, and sanitation services for all. So what does this mean? We are running behind in terms of, in the 21st century, with so much advancement in terms of science and technology, we as humankind, as governments, as institutions, we are still running behind provision of clean water. And this means water that can be drunk from the tap. UN, in this slide that presents some gross estimates from 2017, estimate that the amount was about 2.2 billion people, which is already a very large amount. However, nobody in the developing countries, except for very, very few cities, have access to clean water. So that means that this figure of 2.2 billion people increases to 4 or to more. In the case of sanitation, it is even more if we consider all the cities that don't have a treatment of wastewater and safe disposal. Now, with COVID, the biggest disruption in our lifetime, we learned, and it has been documented, that about 50% of medical facilities in the world do not have water and do not have soap. So the situation is worse than what we thought. And this specific slide focuses only on COVID, but this is about life, this is about development, and it is about opportunities. There is no clean water available and sanitation services for more than 50 or 60% of overall population. And again, I come back to my question, how can artificial intelligence help us towards not solve this problem? This problem is very complex, but towards establish several steps towards its solution. If we go to the next slide, I reflect again on who are all, because the Sustainable Development Goals said that this is clean water and sanitation for all. All means many people. All means about 7.5 billion people in completely different geographies, different climate, different policies, politics. And as we can see, the starting point to have water, which is rainfall, varies, and varies dramatically in different parts of the world. We see that Australia, that has one of the best systems in the world, is also very arid. So that means they have better institutions and better management. And so is the case in the western part of the United States, but it's not the case in many other places in the world. And if we can see the next slide, please. What we see also is that this water that is scarce is also scarce not only because of lack of precipitation, but it's scarce because of pollution. Most of the water in the world, most of the rivers and aquifers in the world are polluted. They are polluted mostly in developed countries, mostly because of agricultural runoff. And in the case of the rest of the world, the developing world, for point sources of pollution. So that means that we have our sources of water are scarce, are polluted, and our population is very large. Again, what do we do with artificial intelligence? How can it help us so that our decisions, the human decisions, the human intelligence can be better? And we go to the next slide, please. And again, what we see within this overall context is and I'm going to refer to two studies that have been done on applications of artificial intelligence in the water sector. One of them is by UNU INVE, and they identify, well, I was part of the study, identify several very broad areas for which artificial intelligence is being useful. Forecasting, for example, water demand and consumption, but in general forecasting. Prediction, for example, in terms of maintenance of water infrastructure. Monitoring, not only water quality, but also in terms of prediction of water-related disasters, or, as some of my geography friends would say, natural events, not necessarily water disasters. And also in terms of monitoring health and environmental impacts of water reservoirs and dams. So these tools we have that are recognition, learning, drawing conclusions, making predictions, and helping to take actions are being used in some parts in the world. This is not widespread all over the world or in all countries, not even in all developed countries. This is only in some places. Another study that is in the next slide is that by the Asian Development Bank. If we can see the next slide, please. So what we have is the Asian Development Bank, and they focus basically on water utilities. So they say the benefits for water utilities of artificial intelligence is in terms, as we know, of maximizing information and data available, and this is for better decision making, to improve performance and quality of the services. However, we go back to the information and data part. Data is not available everywhere. Quality of data many times is questionable, and we all see it in the global studies where the world is mapped in 2-3 pieces, and then assumptions are made or predictions, general predictions are made. And many times the information is wrong because we lose the local context. So this would be the case for water utilities that already have the data, that are collecting the data, that know how to analyze it, and the same with information, and that have an institution that makes use of it. Because many times we have this data under different departments and the departments don't communicate with each other. So more than the sole availability of data is necessary. But the policy considerations that the Asian Development Bank identifies are not different in water, are not different from other areas, which are ethics and governance. The protection of personal financial data, in this case for consumers and for the water utilities. Regulations. Artificial intelligence needs to be regulated because it opens many possibilities. Every possibility should be regulated so that it is more beneficial. Technical and financial policies. Technical policies, because the code of practices, as well as every other technical instrument we have so far, needs to be updated. And financial policies, because different or new financing instruments are necessary precisely to finance these new artificial intelligence related initiatives. In the next slide, please, continue with the same idea. We see, I'm going to mention 2 examples briefly. Who is using artificial intelligence? These are in Asia. One of them is China. The other example will be Singapore. So what does China say in this new generation of artificial development plan? So what this plan explains is that artificial intelligence has become a new engine of economic development, and that brings numerous opportunities for social construction. However, that there are important gaps. And this is not only in China, this is all over the world. There are important gaps in terms of basic theories and in terms of knowledge, core algorithms, key equipment, chips, products. So when we talk about artificial intelligence, we have, again, to put it in context, it's not changing the world. Those figures in billions that we read mainly in the press or by consultants, that the artificial intelligence has certain potential. It will depend. It will depend on what we have and on the institutions that are able to use them. China also recognizes that this linkage, this cooperation between the companies, the industry, and the academia still has to be developed, and that the talent, this talent the world is requesting is still in amount that is necessary, and that infrastructure, policies, and regulations, again, as mentioned before, they are essential for the widespread use of artificial intelligence. In the next slide, I present the example of Singapore, the next and the others. So Singapore is an excellent example where technology, not only this, but technology is recognized as a means to an end, never as an end. The end is always socioeconomic development of Singapore. And the means in this case will be artificial intelligence. How is this technology used? So the Smart City program, it requires of this national, or has developed this national artificial intelligence strategy that covers 5 areas. The second one, that is the one on the municipal services, that one is water. But what is very important is that Singapore recognizes enablers. So we need certain circumstances so that artificial intelligence can be made more effective or can actually happen. As China mentioned before in the plan, this is about collaboration. Industry, research, government, talent, data architecture, which is very important. And within the data architecture is where not only data is collected and used, but privacy. And we have international collaboration. We have that it has to be in a trusted environment. So we require more than the technology. The next slide also that refers to Singapore. What we see is what are the 3 points, important points that Singapore considers for this national program. In order to develop research capabilities and become the leader by a certain year, as China has announced, as US has the intention to be, you require to build your know-how, your knowledge, which is the technology and the algorithms. However, you also have to have your focus very clear, which is, in the case of Singapore, and it should be all over, for broad economic and social development, to create impact. And finally, to be able to implement it. Theory is as good as you can implement it. And so this is the environment of Singapore. If we see the next slide, please. We come back to sustainable development goals on clean water and sanitation. In order to achieve or to come closer to our goals, which is provide clean water and sanitation for all, which means for these 7.7 billion people, we need to improve access to safe drinking water and sanitation. For this, we require better quality water monitoring and quality, conservation and reuse, reduce water impacts from energy production, also from agriculture contamination because of the runoff. We need to improve resilience. This resilience we have been talking about for years because of climate change. And this is in terms of social, economic, and environmental aspects, precisely because of impacts of climate variability and change. But now we see it because of disruptors like COVID, for example. The world was just unprepared for this situation. And a service as basic as clean water and sanitation that was not available before, it has become, the problems have exacerbated with COVID, with climate change. Will one technology be able to solve it? No, of course not. This is one of the many technologies, one of the many that has to be used within a management program, within overall framework for development. And if we can see the last slide, please. This is basically the one with which I finish. Let's remember that artificial intelligence is this technology, this tool that helps improve decision-making in order to provide clean water, drinking quality, and sanitation, wastewater, proper treatment and disposal for all, this is for 7.7 billion people or more, we have to improve decision making. And this is still human decision making. And with this, I close my presentation. Thank you again for the invitation to participate today.
Thank you very much, Cecilia. Okay, again, let's open the floor for those that want to raise any question or ask you for any clarification about your talk. And I don't see any at the moment, so I will step in and ask you to comment on the application of artificial intelligence models in countries in which data are not so available. You mentioned in your talk that artificial intelligence can promote sustainable development goals, but I wonder whether these models require a lot of data, and that might be a limitation in many contexts. Would you comment on that, please?
Yes, thank you, Alberto, for the question, and that is very pertinent. Data is necessary and is not collected, is not available in many places. It's not even now available for monitoring, for example, water quality. So to think that in the most of the developing world, and also some countries in the developed world, that artificial intelligence can be used, that would still not be accurate. The basics, which is, as you have correctly mentioned, data collection, that is still missing, that still doesn't exist. And that is why basic decisions are not taken properly because of lack of data, and because of lack of data, then further analysis.
Mm-hmm. Thank you. Now,
If I may,
yes, please.
If I may, Cecilia, thank you so much.
Yes.
Very interesting, fascinating talk. Thank you so much. I have one question. Assuming resources were available, financial, etc., what Singapore has been able to accomplish, trying to bring observation systems, advanced AI, etc. Is it scalable? Can it be scaled up to other regions of the world? Because after all, Singapore is a relatively small country. Any thoughts on that? Has that been looked at by various agencies that you have been involved with?
Singapore, as you say, is very small, but so one could compare it with another cities, never with a country, but with another cities. And yes, Singapore has advanced tremendously. Singapore by now has a three-dimensional model of Singapore, and that is making decision-making much easier, because then you can construct, right? You can construct and deconstruct because you have the data. But the reason why so much technology has been able to be implemented in Singapore, again, is because it's within this broad framework of development and governance. And there has been an intended effort by the government of more than 15 years to focus on technology. So when you talk about the financial resources, yes, they are necessary, but more than financial resources are needed. You need the government, you need the industry, and Singapore is a hub, as it is called, for on industry, because they know it's very competitive, but you have all type of opportunities to develop ideas. So could this be taken to another place? Yes, I think it could be, but it would have never to duplicate, right? We know that it needs to be adapted, but to consider, you need stable government, you need know-how, and you need this sustainability to which we never put a date, and sustainability has dates, because making it completely open would be very difficult. But you do need these programs that are long-term and that are embedded in your development policies. And then I think it would be possible, because if Singapore has been able to do it, then any other city that is that looks as to the future like Singapore will be able to do it.
Cecilia,
Yes.
one of the attendants, Abdullah Al-Musa, would like to ask a question, and I will convey it to you.
Yes.
Is data security a limiting factor in artificial intelligence application?
Yes, yes. Security, I don't know if the question means if one should have more like cyber security considerations because of you have all this data in one platform. But for example, in the case of Singapore, data is not in one platform. Government agencies are not even connected to internet anymore. I mean, you as an individual, you are connected, but not all the computers, all your equipment that has data is not connected to the internet precisely because of security. And information is divided, is on the office of the Prime Minister, that's it. But otherwise, precisely because of security, is not in one single place.
Cecilia, I was wondering about, you mentioned the ethics, and that's always a common theme when we talk about artificial intelligence.
Yes.
In terms of promoting the SDGs, what kind of ethical questions could arise in applying artificial intelligence to these goals?
I think that the Sustainable Development Goals are well thought. They need to be addressed. So the concerns, the ethical concerns wouldn't be related to them, but more with the use of the data. So if we collect data, and for example, in the case of water utilities or industries, they want to know that their data will be protected because in many of the cases it's proprietary. So they want to know that it won't be disseminated or in an illegal way or without their consent. So rather than being related to the SDG, it would be more the way in which data would be treated.
Mm-hmm. Well, Cecilia, again, thank you very much for your talk. I think artificial intelligence opens all sorts of questions and opportunities to promote SDGs. And certainly the experience accumulated by Singapore has always been a showcase of opportunities to improve the well-being of the population. Thank you very much again for your interesting talk, Cecilia.
Thank you, Alberto.
Excellent. Now we move to the final talk that will be presented by the Rosenberg Forum Chair, Professor Surush Surushian. As he said, he is the Forum Chair and is a distinguished professor of Civil and Environmental Engineering and Earth System Science departments at the University of California, Irvine. Surush, please get on to your talk. Thank you.
Well, thank you so much, Alberto, for the introduction. Let me just again thank everybody for participating. My talk is a little bit closer to maybe perhaps Dara's presentation, while I get a little bit more specific with respect to the observations from satellites and how we use artificial neural network models for precipitation estimation. We always acknowledge the agencies that have supported our research over the years, and I actually present this on behalf of my colleagues at CHRS, which is a center I direct here at UC Irvine. And many of them are, of course, featured in this picture, former students and the current students and colleagues that have been contributing over the years to our work. Dara already mentioned that one of the things that has driven hydrology has been looking at maybe the extremes and also water availability questions. So these are with the excitement some decades ago about the role of climate becoming more visible and important, The type of questions we get as hydrologists are, how will climate change affect precipitation variability and water availability? And can we predict the future changes which are responsive to the user needs? And when I talk about water availability, now that has been expanded not only for the humans, but also with respect to all the categories that Dara presented on his slide, such as the ecological requirements, in-stream requirements, et cetera, et cetera. All right, so moving to the next one, we rely on observations. We learn from the data, and traditionally we have used statistical and extrapolation techniques, and the physical modeling has been instrumental in using those observations to answer some of the hydrologic and water resources questions. And that's featured, of course, also in the models now that has been expanded in the use of climate models or regional climate models in order to get answer to many of the questions with respect to the future. The question is, how reliable are they, and how much one can actually rely on them. My talk, as I said, will focus on the precipitation estimation. And that's been the work of our center for the past 20 years and 10, 12 years before that at the University of Arizona. The way the rain is measured, either through rain gauges, radars being deployed in many places in the world, particularly in the United States. Over 200 radars cover the nation. And then satellites have become also another capability that I think our work will focus on, and I will present some of the advances and actually progress that we made. This figure is an important one. It shows that, as Dara mentioned, gauging the watersheds or regions is not necessarily sophisticated. I mean, it is not necessarily easy, because in order to capture the variability of the rain, you need to put almost a rain gauge every few meters from each other, and that's not possible. If you look at, for instance, the official US gauge coverage for the Western United States, it's about one station per 600 kilometers square for the Colorado River Basin. And most of the gauges are really located in the urban areas, the mountainous areas, which actually where they're more needed because of more precipitation, are rarely covered. Radar has been really great and advanced over the decades, but again, it has its own limitations because it cannot penetrate obstacles such as mountains and hills, etc. And since the rain falls in a higher elevation, sometimes we are not able to capture it. This particular figure that you see shows at the 3 kilometers above the ground level, and those little circles represent how much of the land is being covered by radar in measuring precipitation or signals that are converted to precipitation. If you pay attention to the left figure, I click on it and I drop the beam of the radar to 2 kilometers, you'll see that we have less areas of coverage. And if I go to 1 kilometer, in the Western United States, radars are not as effective as you would like them to be. So therefore, I think satellite is an excellent option that has become available, and that's why government in the US and many others have started putting and investing a lot on the satellite observations. Well, satellite observations, Dara already talked about some of the missions that he's involved with, particularly SMAP. So fortunately, over the past several decades, it's been an international effort by many countries to launch different satellites to measure different things looking at the Earth. Many of that information is, of course, available, and there is, of course, a tremendous amount of data that has been generated, and it's sometimes overwhelming how to use that information in order to convert them to usable and for practice, usable information for practice. As far as remote sensing is concerned, this figure in this range is what our eyes see in the electromagnetic spectrum in terms of the wavelength. But sensors, the way they're designed, may be able to see beyond. Sorry, so whatever happened, I guess. I was mentioning that, the different sensors have the ability to see beyond what human eye can see. And this has really been the backbone of what has driven the advances in the remote sensing area. And if I go, Dara already mentioned the SMAP satellite program that he's been involved with. And let me get my laser pointer back. And there have been quite a few satellites that have focused on precipitation. And SWAT was the one that Dara mentioned is going to be launched by 2020 was the target, but it has shifted for a couple of years. So we have quite a bit of space instruments that are finding their way into our science, and we are using them to our benefit. So when I talk about satellite observations of rainfall estimations, again, some really incredible progress has been made. We have active radars now in space, and this particular mission was launched by NASA with the international collaboration at 2014, which is intended to map global precipitation every 3 hours. So on an interval every 3 hours, we will have precipitation estimation coming from this satellite. And sophisticated techniques have been used to try to develop how we can convert those signals into precipitation information. So let me go and describe two types of satellites, sensors we have. One are known as the passive sensors that essentially take the reflection that comes from the sun hitting the earth. It is picked up by the satellite. It is not as effective as if you had a radar in space and you actually send a signal down and got the reflection back, because that shows a higher degree of information and precision. The first one could be compared to when you go these days any place and they sense your temperature. That's kind of a passive approach. But if you go and have a X-ray taken, this could be like it's a active radar approach. Among the many advances that have been made, and I'll talk about those, are that most of the countries have these geostationary satellites that are 35,000 kilometers above the Earth and capture the precipitation and cloud information, mostly in the infrared spectrum of the signal. And US at the present time has two geostationary satellites, goes west and goes east, and one backup one that if any of those go bad, they can actually activate that and gives good coverage. But then it's an international collaboration with other countries that has made this possible. Advances that have been made, these are the older generation of the satellites that were being used by the US. They only had 5 channels, and the current ones have now 16 channels, and they've been launched in recent times. In the electromagnetic spectrum, each one of these bands provides additional information that hopefully will improve the quality of the data that we have. How artificial intelligence plays into this game is the next topic that I will briefly review. Artificial neural networks or AI have been developed as a concept like human brain works in the background. You take different information, you process it, and you take an action. So in fact, for any kind of a system that we have, even though artificial neural networks or AI approaches are black boxes, but we take various inputs that we think are relevant to the issue that we have interest in, and process it through a series of what we call layers, and hopefully get the type of answer we want. As an example here is that if you are interested in traffic conditions and slippery roads, you enter the relevant information that you think will provide enough knowledge about what the conditions are, such as temperature, whether it's raining, etc. The network itself will process these things and give you an indication whether you have to be careful or not, or other hazards in the road. The same concept has been used by us in terms of getting to one of the key requirements in the hydrology, which is precipitation, particularly trying to get it to the resolutions that are important, for instance, to capture a storm like this, which is a very highly concentrated convective type system. So we have worked over the past 20 plus years on something called precipitation estimation, or using remote sensing information, and artificial neural networks, Persian system. And this work was the dissertation work of my colleague, Colleen Xu. So on this side of the diagram is where all the information that comes from the satellite channels is processed through an artificial neural network. We use additional information to calibrate the parameters of this artificial neural network model and generate estimates of precipitation on various timescales, which I'll talk about. More advances in the artificial neural network techniques, deep learning techniques have been coming, and back in 2002, Hong Yang, who's now professor at Oklahoma, developed the concept as a student working with myself and Colleen of trying to classify different clouds in terms of how much precipitation they provide. That enabled us to get it actually to 4-kilometer resolution. And we've put all that information and those models into work. And at the present time, we have 3 websites, one dealing with climate data set, one dealing with real-time weather scale data set, which is iRain. And we have an app available you can download for your iPhones or Android machines. And finally, the data portal that serves the data free of charge to anyone who is interested. And we have quite a few users for that. The first one is the data that has been put on our rains field, thanks to Professor Fu Wen, who took this project on and created a very user-friendly technique. But the data that is the backbone of this climate data record was the work of Ashuri with Colleen Xu, my colleague, which really has resulted in us developing almost 19 years of climatology of precipitation at 25-kilometer resolution on a daily basis. And now we are moving into more finer resolutions. And the data was requested by NOAA because our algorithm could use artificial neural network techniques using IR channels. And we've been producing this for NOAA and delivering the data to them, but we use it ourselves as well. What are some of the capabilities of this technique? For instance, if you're interested in some region over Sierra Nevada, you can actually go and collect the data and get the entire 38 years of information on a time series. If you're interested in a specific year, you can go to that year. And if you're even further interested in a particular month to look at the information on a daily basis, then you can generate that information as well. These are all built into this rain sphere that I mentioned. For instance, if you're interested in the climatology of California, you go and choose the particular fields that you want, and the tutorial here gives you the guidance how to do it. And you can actually, within seconds, get the information in terms of, let's say, the climatology. And here it shows the histogram of precipitation patterns, which shows no statistically significant decrease of precipitation, but quite a bit of variability. If you like to look at further information, we have created what we call rain trend, and that allows you to look at a global picture of which regions, based on our data from 83 to the present time, have seen trends towards more precipitation versus less precipitation. And as you see, there are certain parts of the world, the blue colors or the colder colors show increasing trend. The warmer colors show decreasing trend. So you can actually go to watershed scale if you wish, and also get more detailed information about the watershed of interest to you. For instance, here is Western United States, Colorado River Basin, that shows there has been definitely a decreasing trend, but not necessarily over California. This is by states over the United States. Again, the same information is easily accessible. And this is again based on the data from 83 to 2019. And every quarter, when the satellite data becomes available, we update it. The Colorado River Basin, for instance, you go to the watershed or major basins, and you will see that, unfortunately, the Colorado River Basin in the past 38 years shows a decreasing trend, which is statistically significant and is of concern. Our real-time data set that is also used extensively is served through our iRain website. Here is an image I took yesterday of the precipitation over the globe over 48-hour accumulations, or you can actually see the development of storms over some regions. This is in Central America that is ongoing as of yesterday, and that sort of tracks the patterns of precipitation from November 28th through December 1st. So these features are helpful. Do you wonder who uses our data? We keep track of it. We have people from 210 countries, and as of present time, about 1 million visits to our site, and this shows how the data download takes place. So there's quite a bit of users we have, and they interact with us a lot of time. So this is, of course, on the observation side, and we see trends, we can analyze those, but a lot of people are interested what happens in the future. I'm not a climate modeler, but one thing I do, and my group does, is to look at how trustworthy are the outputs of climate models, as important as they are in terms of precipitation estimation. These are the results from the latest IPCC work that is going on through CMIP6. And if you look at 4 different models that the data was available, and my colleague Miao in Beijing Normal University helped, the warmer colors show that over the next from 2015 to 2100, whether we have a positive trend of precipitation predicted by the models or not. And you see that the Chinese model shows that Western United States is going to get drier. So is the Japanese model, but Canadian model shows that we are going to get actually wetter. And the other model, the French model, half of the California or northern part of California shows maybe positive trend or southern part. So at this point, these models are not yet consistent in terms of their opinion of what happens. And that makes it difficult for users, particularly for planning purposes. My last slide is much research work is ongoing and will be needed to improve predictions of future regional hydroclimate conditions useful for water resources planning. And I hope this was a useful presentation. At least I introduced some of the data sets that can be used and available to you.
Thank you very much, Ruth. I myself was one of the users of your model, and I can testify that it's really a very good model. So there's one question by David Hill. So Ruth, he writes, there are a number of private sector commercial satellite operations. For example, plant, there are being actively used for commercial processes such as precision agriculture, forestry management. Is there an opportunity to collaborate with or obtain data from them to add to wealth of data that might support better decision making?
David, I'm sure that it is probably possible, but private sector or commercially available information, they have proprietary conditions that unfortunately we cannot follow as a public institution. And my center, CHRS here, and my colleagues, we believe that we have to really use the information and make it freely available for people to use. We have a lot of those groups that also use our data, but I am not sure if we have ever approached any private sector. All we do, we rely on the data that is provided by the various nations and shared, and we get it from the US NOAA, National Oceanic and Atmospheric Administration, and NASA.
Thank you. There seems to be no other question from the audience, but I have another one for you. Which agencies in the US or some other countries are using your models for their competencies or for the roles that they have in various areas related to water management? Could you provide an example of that? Has there been any interest?
Sure. So we collaborate with UNESCO, and our data is made available through a program of UNESCO called GWADI. For instance, we know our real-time data is used by Namibia for their daily forecast issues. Some other countries, because we don't even have a registration for our data because we don't want to intimidate people not to come in. All we see is how many people come and use our data. When there is a problem, Dan Braithwaite, who manages our data, or myself, Colleen, or Fu here from them, saying that they couldn't download the data. So that's all we know. The rest of it is really what is appearing in the publications. In terms of our climate data that I mentioned, it was published in Bulletin of American Meteorological in 2015. In these 5 years, it's one of the highly cited papers. And there are at least 400 citations to the data set for various applications. Interestingly enough, the last request myself and Fu received was from BBC, their Planet Earth program with David Atherton. They're putting something in Africa, and they wanted to have the precipitation information in the Zambezi Basin because they wanted to see how in the past the migration of birds as well as the breeding has changed. So we provided them that information. Those are also the type of requests we get.
Thank you. One final question before turning over to June and Lucia, who will moderate the discussion. Suruj, you always put a photo of your collaborators, and I wonder from which field do you attract your students? Which are the backgrounds that they come to work with you with? What are the areas and research on academic fields from which you attract students?
Well, the good news is that we get a lot of students, of course, with their engineering interest or earth science interest, and lately even from sort of the ecological side and data sciences as well. So they come, but they have to become trained in hydrology and water resources. That's the good news. There is no shortage of excellent students that we have. The bad news is that in recent years, particularly as we are trying to combine the power of machine learning in processing these kinds of data, they become very good in data science. Of the past 5 or 6 of the graduates of our our group at CHRS, 3 or 4 of them had ended up working for Facebook, okay, Uber, and companies like that, because of course the pay scale is quite different than what they would make as a water resources person.
Thank you very much. Okay, so now I'll hand over to you and Lucia to moderate the discussion for all the speakers. And thank you very much. And Lucia, Yoon, the floor is yours. Thank you very much.
Thank you, Alberto, and thank you the 3 speakers for the very interesting presentations. From different perspectives, there is a lot of food for thought thoughts in these talks. So I just would like to remember how this question and answer session works. Please write your questions in the chat, and you might also ask your question live, and so you have to specify that in the chat, in the specific chat for question and answers. So maybe to start, I think just before moving to, there is a question that remained unanswered. I'm not sure to who might feel comfortable replying. That is a question from Pradeep Day. It's about whether is it possible to use artificial intelligence to address that interoperability. I understand with that this person refers to the capability of different data producers to communicate without a lot of human intervention. So that's one question maybe Shurus or Cecilia might want to answer. But before that, I just want to show, the technical support is showing on the screen the answers that have been posted in the chat to the questions that we posed at the beginning of this event. So here we can see some examples of use of artificial intelligence. For example, they're related to modeling of rainfall and forecasts. Weather for hydrological forecast is also related to the processes in water treatment plants. I would add that to that also the use, for example, for hydrological survey. I'm aware that there are studies that try to combine different hydrological data, so geological data, to identify areas where there is a good potential of finding groundwater for exploitation. And well, and in terms of the second question, what research questions have been answered using artificial intelligence? Well, I think it reflects quite well for what I can see the answers related answered in question 1. Anyway, this document will be made available, I think, in the chat in case someone is interested in consulting the responses, replies that we received. So I don't know whether Surush or Cecilia would like to address the question that was posted in the question and answer chat about the capability of artificial intelligence to address data interoperability.
Well, you know, if there is enough data that are relevant to the issues of operability, you know, machine learning is really a mechanism by which it can process large amounts of information and try to organize it in a way that it makes sense, but it has to be benchmarked against some observations to gain trust. So I'm not so sure if I'm answering it, but at the end, it is not a magical way to create information. You need to have something as input in order to use the capabilities of artificial neural networks or AI in order to process the data. Maybe Yoon Duan can probably comment on this as well, or others who are on the call. You're mute, Yoon.
Oh, okay. Yeah, say the question again.
The question, I think,
Well, Yes, it's possible to use artificial intelligence to address data interoperability.
Data interoperability. I think the advantage of AI is they can treat different source of data, different type of data, and maybe I still trying to understand what interoperability mean, but from what I understand of the capability of AI is they are able to handle different source of information, and one of the problem I'm working on right now is like we have models common, like global models, regional models, and models with like 200-kilometer resolution, and the models with like 10-kilometer resolution. You can mix all those different kind of information together, and that's what I understand of the capability of AI.
Okay, thank you, Johan and Shurush. Maybe before, while people can write questions in the chat, in the question and answer chat, I have a question for Shurush and Cecilia, and I think it's relevant. They showed very different perspectives about the same topic, and my question to both of them is: so if looking from your perspective, so more a social science, Cecilia, and more a hard data science, Shurush. I think there is always an issue with data and techniques like artificial intelligence to get down to really be helpful for decision making and eventually improving decision and achieving those development goals that have been presented by Cecilia. So my question for you is, what do you think should be a priority, something that, from where to start, because I think you are still far from really being able to use all this type of information, all this type of data and these techniques for solving problems, in a systematic way. So what do you think would be the priority in order to get closer to that use or usability of these new tools?
Okay, Cecilia, you want to go first, or shall I?
Yes, thank you. I always give priority to institutions, Lucia, because if you have institutions that are operational, that are managed properly, where you have a plan, where you have a plan that works, for example. I mean, not any plan, like in Singapore, any policy, any plan is made thinking that it will be operational. So if you have an institution that is within a frame, an institution that is efficient, that is not corrupt, or you have good people, then you are able to utilize different instruments. Artificial intelligence, one of them, numerous types of technology, the different ones. But for those countries, those cities that don't have institutions, then there are many problems. And forget about the resilient part, is operational institutions. Then how can you implement and take forward the decisions that are taken? Because it's not one person, but it's by the institutions taking decisions, then the impact is very large. Your policy can reach the entire city or the entire country. But if the institution is not operational, then these decisions will not be implemented. So I will leave my comments there.
Thank you, Cecilia.
Just adding a little bit to what Cecilia said, beside the institutional frameworks. In order to really convince planners and decision makers that such information is useful, you have to demonstrate to some extent the reliability and convince them it's perhaps a good replacement for some of the more traditional ways that they've been making decisions. We see that that's a slow process. It takes time. You have to build that confidence. And frankly, a lot of this new stuff that is introduced, the technologies, models, etc., you have to be very careful not to be aggressive in terms of pushing their deployment, I come from Iran by background. I'm very sensitive to how developing countries have introduced new tools and technologies in many regions of the world, which really haven't been necessarily tested in their own developed environments. We see a lot of these models being promoted in Africa for disk management, drought management, for flood management, etc. And I always say that, frankly, that capability has to be built internally, not for a bunch of consultants to come and actually do things for you. So it's just the same old stuff. In the United States, for instance, there have been a lot of advances in distributed hydrologic modeling for flood forecasting. But when it comes to the use of those, still there is a hesitation by river forecast centers that are actually in the business of issuing forecasts to move to the newer models because they feel comfortable and confident of what they have, which are the older versions. So I think it's a generational thing.
Thank you, Shurush. Do another one if you want to add something or?
Yeah, let me be like a audience ask a question for Cecilia. The artificial intelligence. You mentioned the education is probably one of the very important aspect. People have to work on. Because like it's artificial intelligence needs a lot of technical education, for the managers or even for the stakeholders. So that means in the those probably it goes back to the previous question. You're going to see a gap. This is like for the challenge for the SDP kind of thing. Trying to achieve equity, trying to. So can you comment on right now introducing this AI? How far can we achieve the equity for different countries with different level of development?
You have mentioned something very important, which is equity.
Cecilia, can you have the mic closer because we can hardly hear?
Yes, of course. I'm sorry for that.
That's
I think you will be able to hear me now better.
Yes, a lot better.
Thank you. The topic of equity is very important, and I don't see how artificial intelligence can contribute to it yet. And this relates very much to what you had mentioned, which is the education, for example. The education is needed in many fronts. Education, training, one of them, because people that, if the governments want to go ahead with artificial intelligence in different ways, they have to train people. But exactly from the managers. So as Soru says, they see this potential. But it's also the people that will lose their jobs because you are introducing artificial intelligence. And what do we have? Again, my example is Singapore. For the last years, there has been retraining for everybody. Every Singaporean who wants to be retrained will have education paid because the government knows that every time there is these vehicles, these taxis, we're thinking of taxis, vehicles that are unmanned, you will lose workforce, and that workforce will end up in the street, and you don't want that. So you retrain them. So there is a massive effort of retraining millions of people. Can this be used and implemented somewhere else? The idea, because we go very far in introducing artificial intelligence, and then you have all the social impacts that have an effect in terms of equity, and you don't consider them. So rather than seeing the artificial intelligence by itself, and this is a topic that has been discussed very much, by itself, the benefits it has, perhaps to see it with a 360-degree angle, all the potential, all the risk, and then you address them. and you implement artificial intelligence in the way that you can implement it. Otherwise, you don't, because then you have more social impacts, right? And what Soroush said, I am from Mexico, so I have exactly the same viewpoint. We have to use in developing countries what we should use in order to develop further, no more. And if our technology still is at a different level, then we should continue with that technology until we master it and we go to the next level. So coming back to artificial intelligence, I think is one more technology that opens opportunities for the cities that are able to do it. But that is not everywhere, and we shouldn't push it everywhere or consider that it's less developed because it cannot be done. Everything is a matter of development, and cities, if they are at a different level of development, they will be able to implement something different, and that would be okay as long as it improves socially and economically.
All right, great. So Lucia, you want to wrap up, or we can hand it to
there is one hand up. There is somebody has his. It's M. Donoso.
Yeah, but
do you?
Yes, I think we asked to use the question and answer chat. So I'm not sure Donoso is interested.
I've promoted him, so he
okay.
can question.
Hi, do you hear me?
Of course. Yes. How are you?
Hi, thank you, Soroush. Good to see you and all your team, and congratulations, great event once more. I apologize, but my camera is a little bit defective, so I'll just like to add to what you just mentioned in terms of specifically the introduction of technologies, but most important models into developing countries. And I've worked in the last 10 years in numerous countries in Africa, and it was very depressing to see announcements of the course, a short course of 1.5 days, for example, on the Model X, and I'm not going to mention what model, but today Model X, tomorrow Model Y, and promising that after that short course, they will be fully capable to use their models for managing water resources or performing climate-related predictions. And I think that it is the responsibility of the scientific community to somehow intervene and bring to the attention of these types of initiatives, which are in some cases really costly. I mean, in an average capital of say East African country, a seminar in a hotel, and I'm not saying the Hilton or any big hotel, costs of the order of $10,000 to $15,000 to bring in people and provide the facilities, translations in some cases, and you can pay a number of students to do a master's in a local university for that amount. So I think we don't usually talk about this, but it is, I believe, our responsibility to really denunciate these kinds of issues, because it's hurting the country, is hurting the water community in general, and it's not benefiting or improving at all the situation of water resources in these regions. Thank you for the opportunity to say this. Thank you. Bye-bye.
Thank you, Maria.
So thank you, Maria. And I think, so there was one question that was posed from the poll, automatic poll. So please reply to this question. And I think Soroush will wrap up and maybe also comment on the answers we received to that poll. So thank you, everyone, to participants for this interesting session and for sharing your knowledge with us.
Well, for my part, I really appreciate Lucia and Duan for managing the question and answers, and Alberto for your skillful approach of managing the presentation. Cecilia, thank you so much for your presentation. I know you've been in transition and move, and we are delighted that you were still able to participate. And Dora, I guess he had to leave, but I thanked him already, and this is great. So here at this point, we are really wrapping up, and there were a few other questions, and the results are in. The answer to the question, do you see the potential of AI in your practice? About 64% of the respondents said yes, a lot. About 36% some. There was nobody that says none. So that's really good. I think in both camps, those that will see a future for this stuff in their data, I'm sure that the others will join, and that's great. I think this is pretty much the end of our second webinar, and I thank everybody, and especially the participants. And I will ask Sherry if there are any final things to talk about.